So for Unit 7, Day 3, with your transformations, we're using the Desmos activity by adjusting the sliders to see what impact the values had in place of A, C, and D on our functions. And a couple of things that we should have realized were that there are input changes and there are output changes that are happening. And so when we're looking at these values, the output changes came from A and D, and the input changes came from C, because C is with the input of X, A and D are outside of that. Now, output changes, those are vertical changes. We had stretches and shifts going on. Input changes are also shifts as well. So when we're talking about the transformations of your functions, we kind of think of it this way. And quadratics have a B value of 1, just to keep that in mind. So the output changes came from A and D, and A was stretching, either faster or slower. It made it wide or narrow, depending on the value of A. And if A was negative, that was a reflection over the x-axis. When A was greater than 1, it was faster than before, so it became narrower. When it was between 0 and 1, it was wider because it's slower. D was a vertical shift up if it was positive, or down if it was negative. Now, for the input changes here, for C values, again, that's horizontal shifting left or right, and it was the inverse of what you thought it would be. If you saw a +4, that meant it moved to the left 4 units. And if you saw a -4, it moved to the right 4 units. Again, it's the inverse of what you think. Going back to when we looked at our factored forms of the equations, we had to take each factor and set them equal to 0 and undo it to find the value for x. Same thing here. You have to think, how am I undoing that operation to find the value that we're using? So if we see a plus, again, the inverse goes left. You see a minus, the inverse goes right. Now we had you do a card sort, matching up some functions here with their transformations, and these are the results that we should have gotten. And again, talking about the A values that would happen with your function of 1/2 x squared and the negative x squared. Negative x squared is the reflection. 1/2 became wider because it's increasing slower. 2x squared, 2 times faster, so it was narrower. When we're talking about some input changes, the quantity x minus 4 squared, we saw it move to the right 4 units. Quantity x plus 6 squared going to the left 6 units. Then we talked about some vertical shifting, x squared plus 3 moving up 3 units. X squared minus 5 going down 5 units. And then we had some combos here, x plus 6 squared minus 5 going to the left 6 units, down 5. And then a quantity x minus 1 squared plus 2 going to the right 1 and up 2 units. Then we asked you a couple things about this one function here, describing how it changed. The parent function x squared is here in blue, and our transformed equation is x minus 3 squared plus 4. If you just look at the vertex for each of these functions, right, it's normally at 0, 0. Now we can see that the vertex is at 3, 4. We know that the vertex had to move to the right 3 units and up 4 units to get to its new location. So we have a horizontal shift and a vertical shift. So horizontal shift to the right 3 and vertical shift up 4. All of those items could be written here and be correct. And again, where's the vertex located? That is at 3, 4. It's referred to as a turning point. We also can talk about it being the minimum value, right? The lowest the graph is going for your function. So why are these transformations important? If we know where the parent function x squared is, if we write it in this transformation format, we can automatically figure out where the vertex is, draw our new graph based on the transformations being made, just by knowing the original. So again, talking about your transformations, we had input changes and output changes. So if we think about the table of values, input changes impact your x, so they would be applied to those original x values for your parent function x squared. output changes would happen to your outputs. I'm pointing to the wrong part of the graph. Here's your output changes, your A and D. So again, those are your f of x's, the outputs. Here's your input changes, impacts your x's, your inputs. And we use the values of the parent function here, right, and perform the transformations on them. For example, here's our parent function x squared. I have that table right here built, and that's standard, and we used that before in our Desmos activity. Now here's the transformed equation, x plus 1 squared minus 7. If we can identify the transformations, we can apply it to the table and generate the graph to represent it. So let's think about this. How many transformations do you see in the new function compared to the old? Well, I see two differences. I see this plus 1 and I see this minus 7. So there are two transformations happening. What's the first transformation that's happening? Well, the plus 1. And so what is that plus 1 telling us? Well, it's telling us that we have a horizontal shift. In which way are we shifting? Because it's plus, we know we're going to the left 1 unit. So I'm going to take all of these input values and shift them to the left 1 unit. Operationally, what does that mean? We're taking away 1 from each of the input values from where we were before. So again, we're moving everything to the left 1 unit. So if we're at -3, it's now at -4. -2 is now -3. -1, -2, and so on. Everything is being moved to the left 1 unit from where it was before. The second transformation we said was going to come from that -7. That's going to be an output change. So it's going to be something vertically happening. And so since it is a -7, we are going to be shifting all of the outputs down 7 units. I'm going to take all these existing outputs and move them down 7 units from where they were before. So operationally, we're taking away 7 from each of those original outputs. So 9 minus 7 brings us to 2. 4 minus 7, -3. 1 minus 7, -6, and so on. Moving it 7 down from where it was previously. So we've performed all the transformations. What kind of graph can we generate? Well, the graph is going to come from our outermost columns. So the shifting of the left 1, these are now all the inputs, and going down 7 units, shifting down, those are their corresponding outputs. So I would plot the point, -4, 2, -3, 3, -2, 6, -1, -7, 0, -6, 1, -3, 2, -2 to generate the graph for my function. And once I have my graph, just like I did before, I could identify the vertex, the turning point, and I can see that it's at -1, -7. And I also can identify any other key features for intercepts, x-intercepts or y-intercepts. I can see that they do cross the x-axis, just not at a grid point, so I don't want to estimate where those x-intercepts are at this point in time. We'll show you how you can locate those a little bit later on. But I do see I have a y-intercept at 0, -6, and so I can clearly mark that. But again, notice that vertex. Remember, the original vertex is at 0, 0. How did it move? It went to the left 1 and down 7, based on your transformations that we see in the equation. So let's try another one. Here we've got f of x equals x squared. That's our parent function, and that's what our table is representative of. You always start with that in your table. Now here's the transformed equation. 2 times the quantity x minus 4 squared plus 3. So you want to figure out, first of all, how many transformations are happening. So compare the original parent function to your transformed function. We can see that there are 3 changes. The 2, we've got our -4, and the +3. I'm going to go in order from left to right. So the 2, we know that's an output change. It's a multiplier. That's going to be a stretch. Because it's positive, it's a vertical stretch of 2, meaning 2 times faster than it was before. So I'm going to take all of my current outputs and multiply them by 2. Now the other transformation we said, coming from that x minus 4, what's going to happen there? Well, that's going to be a horizontal shift to the right 4 units. Again, the inverse of what you think it is. So I'm going to have to take all of my input values for x and shift them to the right 4 units from where it was before. So again, if you were at -3, go 4 units to the right, where do you end up? If you're at -2, again, go 4 units to the right, where do you end up? We said there was one more transformation to look at, and that was the +3. Again, that's an output change. It's going to be a vertical shift up 3 units. So I'm going to take all of my outputs from where I last left them here and move them up 3 units. So I'm going to add 3 to all of those outputs. We performed all of the transformations. So what do we graph? The outermost columns is what's going to make up the coordinates for our parabola. So my points would be at 1, 21, 2, 11, 3, 5, 4, 3, 5, 5, 6, 11, 7, 21. Now, if we're just doing a scale of 1 here, obviously we can't fit all of those points on our graph. But again, our goal is try to get, 5. If we can get 3 to 5, we should be in good shape. So if I focus on kind of these points like 211 through 611, I should be good to go. 11 is just past where we were for 10, so we could estimate that. Plot our points, we have the shape of our parabola, and then connect them. Again, we can look for identifying features, most importantly, the vertex for this, and our vertex we can see is at 4, 3. Look for any intercepts. We can see we won't have any x-intercepts for this function because we shifted it up away from the x-axis. We know that we will have a y-intercept eventually. We just don't know where it's at, but we could calculate it because we have the equation by putting the input of 0 to see what we get out. We know it's concave up. We can get the axis symmetry. We could talk about domain and range as well. So that's what's nice about using transformations, doing graphs. We just can go back to what we know about the parent function and use that table as our starting point, apply the transformations, and then we have our final graph. Also remember, in this transformation format, we can tell the vertex pretty easily.